All right. I have a fantastic guest that I have been eager to talk to all morning. Ruth Durrer. She's a professor of cosmology at the University of Geneva. She works on cosmic microwave background, brain cosmology, and massive gravity. Ruth, thank you for this. I really appreciate you joining me. How are you doing today?
Fine, thanks for having me.
No, thank you for joining. I'm a sucker for physics stuff, science in general, and so I've wanted to bring on physicists to have conversations about things that are bubbling up in regards to the background that may not necessarily hit the front pages, but have interest one way or the other, or at the very least, people should be interested in one way or the other. Let me start at the very beginning. What, let's say for 2024, in regards to one of the main discoveries in your field of physics, in your field of research, that hasn't necessarily, let's say, hit the main pages of mainstream media, but is very exciting in the physics community that you guys have been paying attention to and have been researching more into?
Well, for us, one of the great events was the launch of the Euclid satellite
Right.
by the European Space Agency. With this satellite is gonna map out the universe out to very, very high, large distances, nearly to the visible horizon. So we will learn a lot about the distribution of galaxies, which again will help us to understand what drives the expansion of the universe, what is this mysterious dark matter or dark energy. So we are extremely excited, and within a month or two, during March, the first results from these satellites will.
Oh, March. So this is coming up soon.
Yes.
Okay. Is dark energy a real thing, or is dark matter a real thing? I mean,
I'm certain it is. Yes.
Wait, you said it one more time. You say you're hoping it is?
No, I'm not hoping.
Oh,
I'm quite certain it is. I mean, dark matter, something like dark matter for sure is there. We know that since about 100 years that the visible matter could not hold clusters of galaxies together, wouldn't make galaxies the way they move. We are quite certain that it would even not have led to the formation of galaxies at all.
Right.
So something like dark matter is out there, but we don't know what it is.
Is it possible that it's a mathematical anomaly and that something else is going on? Either, let's say, for example, like gravity only goes to a certain length and it has a cutoff. Is it possible? I mean, in fact, I think there was either other research that was making this argument that time might have something to do with it. Like, meaning, is it possible that there's something else going on that what's being considered? Okay.
Mm-hmm. Yeah, that's possible. There are some things which are not just, kind of vague speculations, but real physical theories where calculations can be performed. In physics, we don't want just to say this could, that could. We want to have equations which determine, somebody has to say, okay, that's the physical laws which this theory should have. That's the predictions which I make with it. Let's see whether they agree with what we observe. So if dark matter would just be gravitating matter like ordinary matter, it would agree with a lot of observations which we make. Then there are other theories like MOND, where you can get the clustering of galaxies, but you don't get weak lensing observations right, or you don't get the cosmic microwave background right. So it cannot really work out. So there must be
something else.
It must be a bit more complicated than that. But it could still be that there is another solution and it's not dark matter and we just haven't found it,
Because it's very anomalous. I mean, correct me if I'm wrong, it's like 85% of the matter that we see, matter energy, is unseen. It's like only 15% of what,
Yes.
Like everything that we know of in the universe is like 15% of what's there, which is very, it's kind of difficult to get your head around.
Yeah. Actually, what we see is about 5%. What we see,
5%.
what we know about, is about 5% of what's out there. And dark matter is about 25%, and the others, nearly 70%, are dark energy. So
That is
it's very
astonishing.
disturbing. I agree with you.
Yeah, that is pretty astonishing. There's something invisible in our universe that,
Yeah.
the overwhelming majority of the things in our universe that just can't be observed. Have there been any studies or anything that try to observe, might not necessarily be the right word for it, but at the very least to get some kind of experimental evidence beyond mathematical observation?
Um, Of course, there is experimental evidence of this dark energy. Otherwise, we wouldn't be talking about it. And the reason and the observational evidence is that we see that the expansion of the universe is, since about a few billion years, getting faster and faster. Before,
Mhm.
it was doing what we expect, namely gravity is attractive, things attract each other. You're attracted to the chair you're sitting on. We are attracted to the earth, whatever. Gravity is attracting. So we would expect that this explosion from the Big Bang is getting slower and slower due to gravitational attraction. Now it seems to get faster and faster again. So there must be something which we call dark energy, which actually is repulsive under gravity. This can happen if something is very weird, behaving very different from all the particles which we know about.
Mhm.
And for example, if it has a very strong negative pressure. For example, the so-called vacuum energy would have that, and is one of the kind of favored candidates for dark energy. But there are other candidates of what it might be. So it's a very weird thing, something which you don't recognize in your daily life, but which seems to govern the expansion law of the universe. Now you can say, okay, maybe the expansion law or the calculations which led you to an expansion which is slowing down are wrong. But you see, the main assumption there is just that gravity is an attractive force.
Mhm.
And that's all we have seen so far, wherever we have looked. But there in the universe, it seems suddenly to become repulsive. That's the problem of dark energy.
Oh, that is super interesting. Yeah, I've always been fascinated with this, just because I've always been fascinated with this part. If you could, my producer, she had a question. She says, if you could build a space telescope to answer one big question in the universe, what would it be?
Yeah, it would be, what is the origin of dark energy?
Yeah.
Or let's say, what is the origin of this accelerated expansion of the universe? Maybe dark energy is the wrong thing. Maybe the equations of gravity, which we now base on Einstein's general relativity, maybe they don't hold on very, very large scales. Maybe
Mhm.
they don't hold for the cosmos at all. That's also one direction people are looking into in this research.
Oh, basically at a certain scale, gravity drops off, almost like
Yeah,
like a strong nuclear force. Like it's very small distances
yeah,
where it works,
yeah,
and
yeah,
it just
yeah,
drops off.
yeah. This
Um,
is also something people are looking at. Giving the graviton a mass could help doing that, but it's not so easy. It's much easier to give a mass to the photon than to give one to the graviton.
you got to explain something to me. So the thing that has always confused me around this, is gravity really a force? From my understanding, gravity is this kind of permutation of space. It's like, it clumps together around mass. And because it clumps together around mass from the perspective of something that's moving around, it feels like you're either moving down or you're accelerating in a particular direction because of the way space is being warped and shaped. All right. If that is the case, and if there is no it's not space is not really discrete in a way like a particle would be discrete. Space is kind of this kind of continuous thing. Then how do we get a graviton? Like how do we end up with a particle for something that is a curvature of space itself. I never quite understood that.
That's a very good point, actually, which you're making, because if we linearize gravity, if we say, okay, let's look in regions where gravity is relatively weak, and so that's actually most places, then it is very similar to what is electrodynamics, except that the particle of electrodynamics, which is exchanging the electrodynamical forces, the photon, has spin 1 and the graviton is one particle with spin 2. You can
Right.
describe it otherwise quite similarly. On the other hand, where gravity is strong, actually within classical gravity, we assume that that matter actually just curves space-time, and then the laws of gravity tell matter how to move in this space-time, namely moving always along the shortest path now in space and time. So that was the famous saying of John Archibald Wheeler, American physicist, who said, matter tells space-time how to curve, and curved space-time tells matter how to move. That's classical gravity. However, if we want to make a quantum theory out of that, then probably the gravitational field has to be quantized, and the corresponding quanta would then be the gravitons. If we linearize the theory of gravity, we can easily quantize it. But if we don't, then we don't know how to quantize it. Then there is no consistent theory of quantum gravity around.
But that's what I was going to say. There's a contradiction between something on a large scale versus these kind of quantum scales where they don't quite play well together. They haven't necessarily found a theory of everything in order to make these things work. Explain to us why. I remember I was sitting in a physics class and the professor he wanted us to do the equations to show why quantum mechanics and why gravity doesn't work. I mean, or let's say Einstein's relativistic equations, why these things don't necessarily play well with each other.
That's actually, so you have taken a very high level physics class if you learned that, because it's not so easy. The thing is, if we do quantum field theory, we always have to what we call renormalize. This means we have certain quantities which are infinite, but then we say, okay, let's say the electron charge or the electron mass, these are measured quantities. So we can actually absorb this infinity into like 4 measured quantities. And for those, we just say we know they are not infinite, they take this and that value. And even if the result of our calculation would be finite, we would have to renormalize these quantities to the measured quantities. So we do that in quantum field theory, and we are happy. If we want to do the same procedure in gravitational calculations, we see that we have new quantities appearing at every order of our calculations. We are never done. So there are infinitely many infinities. So we can't make sense out of that by saying, okay, we know Newton's constant, we have measured it, that's the constant which describes how fast bodies attract each other, or something like that. A few constants. No, there would be infinitely many of those. So the whole thing doesn't make sense. We can't make any predictions. Because we have infinitely many infinities to absorb, and we don't know how to do that.
And infinities are basically math's way of saying something is wrong.
Yes.
Something is misunderstood. Something is not quite right.
This method doesn't work. So you say, why don't you try another method? We have tried many other methods. So far, we haven't found anything that works. I mean, what I have told you about is perturbative methods for quantum theories. Our usual kind of standard model of particle physics, there the quantum theory which we have developed for that model is a perturbative theory mainly, not only, but mainly. There are other non-perturbative theories like string theory, which might work, but so far we haven't managed to make any meaningful predictions with it.
I am of mind as a string theory has failed. No, I could be wrong on this. I'm not a physicist, so fair enough. You can correct me if I'm wrong. But
Yeah, I don't know.
there seemed to be this big argument in physics right now over whether or not um, 20, 30 years have been wasted on string theory. Because, like I said, they haven't necessarily been able to make these kind of any massive, major predictions. Physics have a tendency to live off of predictions. This idea of, we're going to predict this, and we can experiment in order to discern whether or not the prediction is correct. String theory hasn't been able to do that. I mean, again, correct me if I'm wrong, but you
It
still
has
have
one
people.
nice prediction, kind of. It can predict the entropy of black holes, which is quite amazing.
Uh-huh.
Yeah, which otherwise, I think no other theory can.
I know, but that
So,
could be a quirk. I guess, like, if you only get one. Let me ask you this. Do you think that string theory, there's an argument in physics that the physics community has wasted a lot of time on string theory because it hasn't necessarily been able to, like, that math is not physics. Like, the physical
yeah,
world is different than math.
from a physics point of view, that's right. I mean, one of the reasons I have studied a bit of string theory, but I've never worked really strongly on it because I like to compare my calculations with experiments.
Right.
And if you're a string theorist, you will not be doing that. That's why I find string theory not very attractive. On the other hand, we must be objective about it. It has led to very interesting insights in mathematics. And I mean, there have been 2 or 3 Fields medals, which are more or less for string theory, or have been obtained by string theorists because they could solve very difficult mathematical problems. So it's kind of, as a method, it was a very useful and productive method, especially for mathematics. It didn't make any physics predictions. So, I mean, people who really like physics, who want to calculate something which they then can compare with nature, have gone away from string theory.
Yeah.
And those who still do string theory are mainly mathematicians.
Yeah, I've been fascinated by this fight that's been taking place online in regards to string theory versus regular physics and whatnot. What if you are into cosmic micro background
Microwave
cosmic
background.
microwave background radiation? Can't get it word out. One of the interesting things in Three Body Problem, the book series by what's it, Shishin Liu, I believe is the man's name. Fascinating book. One of the fascinating aspects of it, it's a hard physics book. Like it delves into it's physics triumphalism. Like it takes science and it puts it as like the front bearer of it. This is the reason why I love the book. But one of the aspects of the book was having the CMB blink. Basically, we're going to make the universe blink. Explain to the audience, what is the cosmic microwave? I cannot get that word out. Jesus. Cosmic microwave background radiation. What is that? Just so the audience would know.
Yeah. So in the past, the universe is expanding. So in the past, it was not only much denser, but it was also much hotter. And at some point, it was hot enough that all the matter, the ordinary matter, was ionized. So electrons and protons were not combined to neutral hydrogen or so. They were all ionized. And so photons couldn't travel in this universe. They would always hit an electron or a proton. And at some time, when the universe had cooled down to about 4,000 degrees, matter became neutral. And from there on, photons could travel freely in this universe into our telescopes. These photons have expanded, their wavelength has become longer, they have cooled down, and they are now at the temperature of about 3 degrees Kelvin, which corresponds to about minus 270 degrees Celsius. And we see them. They are in a microwave regime where we observe them. if you would have an old TV set, which maybe your grandparents had uh, with the tubes,
Uh-huh.
you switch that TV set on, you saw, probably you didn't see it, but if you talk to your parents, they might have seen it as children. You
Static.
see white and black dots on the screen if no program is on. When I was a kid, during the day, often there was no TV program. So
Uh,
if you would switch on the TV, there were just black and white dots. And about a few percent of these black and white dots are actually from the cosmic microwave background. People didn't know it at that time, but that's the way it is. It's a rather
that's
strong
what that was
reflection.
from. I had no idea. I mean, look, I am older than I look, apparently. I remember this. We used to have these floor model TVs. They used to be like 500 pounds. These things were huge.
Yeah, yeah.
And it's like if you cut it on, it used to be just static. In the old days, TV didn't used to stay on 24/7. It used to go until like maybe 12 at night or 1 in the morning, and then it used
Exactly.
to go into static. I did not know that. That is what that static is. That's what the static is effectively picking up the
A part
background.
of it, not all of it. There is also noise, and so on and
Mm,
so on. But a part of it is really this cosmic microwave background. So nowadays, to observe this cosmic microwave background, I mean, to just detect it was difficult in the 60s. And the first people who found it, I mean, these were radio astronomers who were working for Bell
mhm.
Telecom Communication, Penzias and Wilson. They got the Nobel Prize for their discovery. It took about 10 years until people believed them. And then they got the Nobel Prize. I mean, they had a paper back to their discovery paper from Princeton physicists who said that this is the cosmic microwave background. But to convince the majority of people took another 10 years.
They didn't believe him. They didn't believe him. They were skeptical
Which
about it.
is fine, one has to be critical. But these two guys, they were looking for something completely else. They wanted to see how how sensitive can they be, can their antennas be, so that one could do satellite transmission for TV programs and stuff like that, and radio programs. That was their idea. That was they were working for Bell Labs, the
Mhm.
telephone company. They were not doing basic research. But they found that their antenna had some additional noise, which they calculated should not be there. And it came from all directions. And what could it be? And so they had no idea what it could be until they were talking about that to their friends. And one of their colleagues said, hey, the Princeton guys are actually looking for something like that. They say there should be an isotropic radiation out there coming from all sides. Maybe that's what you've seen. And it was that.
Wow, that is fascinating. Well, by the way, what is massive gravity? I was looking at your bio. I don't know what that is. What is massive gravity?
So that's exactly the idea that you were talking about, that gravity might turn off at very large scales.
Oh,
If
okay.
the graviton would have a mass, that's what would happen. The gravity would turn off on very large scales larger than the so-called Compton wavelength of this massive graviton. And that's why one of the possibilities for dark energy would be massive gravity.
But okay, correct me if I'm wrong. Anything that doesn't have mass travels at the speed of light.
Yep.
Um, it is believed that particles can't necessarily. Okay, I'm saying this weird. It's believed that a particle with mass can travel close to the speed of light, meaning you can calculate it like 99.99999, whatever that number is, without it ever hitting the speed of light because it has mass associated with it. But from my understanding, space, we don't know whether or not space can move faster than that. Like if you're talking about like a warp drive, for example, and you can kind of warp space and just move space along. If gravity has a mass, would that be true? The mass thing still throws me. I have a hard time wrapping my head around this notion of a graviton. I don't know. I have a hard time wrapping my head around it. But what
Yeah.
are the chances of it having mass? I mean, what's the expectation around it?
I mean, if the graviton has a mass, this mass has to be very, very tiny, because we have seen gravitational waves that would be propagating gravitons, the gravitational waves. And we have seen with this one event, which LIGO has seen, where they saw electromagnetic, so did counterpart, because it was two neutron stars which were spiraling into each other. So they have seen also an optical signal, a signal from photons, and to about 17 decimals, the photons, which are massless to a very high degree, traveled with the same speed as the gravitons. So
Interesting.
So if the gravitons have a mass, it must be very, very, very tiny.
Well,
Otherwise, they wouldn't have arrived in our telescopes at the same time as the photons.
well, that's what I was going to say. If they arrived at the same time as the light, then they wouldn't have a mass, right? I mean, if they were traveling, meaning if the light is traveling,
same time, there is always, every measurement has an error,
That's true.
So
Wow,
same time, plus minus a tiny, tiny little bit. So we can have a tiny, tiny little mass.
Oh, that is fascinating. If it was going like 99.99999 times the speed of light, then we wouldn't be able to perceive the difference in those things. Oh, that is fascinating. Last question before I let you go. Have you watched this kind of scientific denialism that's been popping up with people like flat earthers? For whatever reason, this is a new thing, or this seems to be a resurgent thing. People saying that the earth is flat. People being brave enough to go on YouTube, having their own little flat earth community. People who, Terrence Howard recently said like 1 + 1 is 2, or I'm sorry, 1 × 1 is 2. And people were like, wow, that guy is saying some hard stuff. And it's like, okay, these people are saying nonsense. Have you been, like, where do you think this is coming from? I guess, first of all, and have you been somewhat disheartened by, I guess, the fact that they have their own little corner of the world where they kind of propagate what amounts to honest, just straight out nonsense?
I'm sorry, but the flat earth community is probably just straight out nonsense, no? I mean, come on.
They believe it. They are full, like they are true believers.
Yeah. But these are weird people, no?
It is bizarre. I don't get it.
I can't. I mean, we have pictures of the Earth from satellites where we see the ball, and
well, see, they would say it was like, well, that's a optical illusion. That's what they would say. That's an optical illusion. Or they would say there's a grand conspiracy that NASA is not showing us all of the pictures and images. It is, even if you send them to Antarctica.
Still doesn't. Yeah. Anyway, I mean, honestly, I think, for me at least, don't take me wrong, everybody can do whatever they want. But for me, my life is too short to discuss with them.
Fair enough. Fair enough.
On the other hand, there are mathematical models where 1 + 1 is equal 0. For example, if you look at everything modulo 2, then 1 + 1 modulo 2 is 0. So this is a very useful system of calculations which you can use for certain things, and which does makes completely its own sense. Yeah. Now, 1 × 1 = 2. I have never heard about that. I don't know whether that works in some sense. But there, with different mathematics, there are different mathematics which can make sense, and so you just have to define them correctly and consistently, and then why not?
Last question. I got to get one more in. Has there been anything that has come out, let's say experimentally, study-wise, that has given a result that was not expected? Like, and the result was so not expected that there was the belief that new physics may be emergent, or maybe indicated in that result.
Oh, yes. I mean, for example, the entire accelerated expansion of the universe. These people went out to measure the exact value of the deceleration.
Oh,
And then they
oh, they
said,
went for
oh,
the opposite. Oh,
oh shoot,
wow.
it's accelerating. What's that? At the beginning, everything said, be careful, make a better measurement, don't make silly mistakes. It cannot be accelerating. This must be wrong. And they went on, and there were different groups finding the same thing. And finally, people said, okay, yeah, you must be right. It is accelerating. And the three main initial groups who found it got the Nobel Prize for it in 2011. That was totally unexpected.
Interesting. Do they think, so what is the expectation? That it's going to expand up until a point and crunch? Do they think it's just going to expand forever? Like, what are the models?
Some models say yes, it's going to be expanding faster and faster and faster forever. And in a couple billion years or so, all galaxies are far away. Nobody can do cosmology because we just see the local group of galaxies which is attracted gravitationally to us, and all the other galaxies have moved out of our horizon, and we will not see them anymore. Or there would be possibilities that this acceleration stops again, and the universe will be decelerating again, or even collapsing. It's not clear what's going to happen. There are different models, and in the simplest one, what I said first is going to happen, but this is also a very weird model and doesn't make much sense. So,
but the expansion doesn't take place like between, let's say, Earth and Mars,
no,
or does it?
No. It actually, we are here in the first of all, there is the Milky Way, the solar system, which is inside the Milky Way, and that's a gravitationally bound system. Also, our neighbor galaxy, the Andromeda, is also gravitationally bound to us. The Magellanic Clouds and many small galaxies around us are gravitationally bound together, and do not partake in the expansion of the universe. But
Interesting.
there are two big galaxies, Andromeda and us, and many smaller ones, and all the other big galaxies are receding away from us.
Okay, so we at the very least will be able to stay in contact with Andromeda, with Magellanic Cloud, with basically the things that are in our gravitational orbit or things that we're locked in gravitationally. But everything else is just eventually going to redshift and go far, far away from us.
Yeah.
Ruth, Professor, thank you for this. I am fascinated by this. This is fantastic, and I'm hoping my audience also loved it. They know I am a sucker for this stuff, and I've been trying to get a physicist on for a while. So thank you for this, Professor Ruth Durrer. Am I pronouncing that last name correct? Durrer?
No, it's Durrer.
Durrer. Durrer.
Durrer. Yeah. Okay, that's a Swiss name.
Okay, Professor Ruth Durrer. She is professor of cosmology at the University of Geneva. She works in cosmic microwave background radiation, brain cosmology, and massive gravity. Thank you for this. I really hope you join me again, that this wasn't too painful, me beating you over the head with questions.
It wasn't painful at all. It was fun.
Thank you.
It was nice meeting you.
Nice meeting you. Thank you for this. You have a good one.
Bye. Have a good time.